Hello, welcome to a new unit on functions. Today we are going to see a short introduction in which we are going to give an example of function involving natural numbers. The requirements that we need today are very few. Know the natural numbers and to know how to add the natural numbers. Let's start the unit with a problem. We want to calculate the sum of the first n natural numbers. That is, we want to do the sum of 1 plus 2 plus 3 plus 4 up to the natural number n. Well, this is a classical problem, and it has an anecdote involving the mathematician Friedrich Gauss. The anecdote goes that the teacher, when Gauss was approximately 9 years old, asked them to add the first 100 natural numbers. A few minutes later, Gauss replied, 5,050. How did he do it? Let's try to deduce how he did it. First of all, let's assume that n is a small number, that n is just 10. So, the previous sum would consist of adding 1, 2, 3, 4 up to 10. There is a direct way to do it. We take a calculator, we add up all the numbers, and you will see that at the end you get 55. Why don't we do it in a slightly more optimal way? If we want to calculate the first 10 natural numbers, the sum of the 10 first natural numbers, what we could do is add them up so that it's easier to solve the exercise at the end. How can we do this? Look, we have that 1 plus 10 equals 11. We also have that if we take 2 and 9 also add 11, the 3 and 8 add 11, the 4 and 7 add 11, and finally 5 and 6 add 11. Now it would only be a matter of adding up these new results. The sum would be 11 plus 11 plus 11 plus 11 plus 11 5 times. 11 multiplied by 5 gives us 55. The trick here has been to add the numbers in such a way that the sum is easy, and then add up the results. Now, what happens if n is equal to 100? Let's use the same technique. We want to add up the first 100 natural numbers. 1 plus 2 plus 98 plus 99 plus 100, right? Notice now that 1 plus 100 is 101, that 2 plus 99 is also 101, that 3 plus 98 is 101. And if we continue progressively, we will arrive at the end that 50 plus 51 is 101. That is, the sum requested would be 101 plus 101 plus 101. The question would be now, how many times have we added up 101? If you look a little bit, we have here 50 rows, which are, as you can see, numbered by the first value of the sum. That is the first one, 1, 2, 3, and so on up to 50. We have added 50 times the number 101. So here we can abbreviate this sum as follows. That's 101 by 50. And the multiplication is very simple. It is 5,050. This way of adding is what Gauss did in the anecdote and therefore was able to give the result very quickly. So, is there a formula for this expression? Yes, there is. If we notice, here we have 101 and 50. In fact, 101 is the number n plus 1, and 50 is also very easy to deduce. It is the number n, 100 divided by 2. If we write the formula, you have it here on the screen. It is simply the last natural number that we want to add, times n plus 1 divided by 2. We are going to try to demonstrate this formula, although it has been seen so far in a very visual way. We are going to try to demonstrate it. Let's assume that we know the value of s, which is the sum of 1 plus 2 plus 3 plus 4 up to n. I have added two more terms, which are n minus 2 and n minus 1, which are the two numbers before n. As you know, the addition of natural numbers has the commutative property. That means that we could add the sum backwards. First the n, then the n minus 1, then n minus 2, and so on up to 1. If we now add these two equalities, we have that from the first part, the part on the left, s plus s would be 2s. And the other part, let's add it up by columns. Look. As I said before, here we have 2s of s plus s. And let's add it by columns. 1 plus n is n plus 1. If you notice, 2 plus n minus 1 is also n plus 1. 3 plus n minus 2 is also n plus 1. So, we add up by columns until the last term, which would be n plus 1 as well. How many times have we added n plus 1? Now we cannot look at the rows, but let's look at the columns. 1 plus n would be the first sum, this would be the second sum. 3 plus n minus 2 would be the third sum. In a way, these numbers also indicate the number of sums that we do. 1, 2, 3, 4, up to n. Therefore, we have made n sums. We have added n plus 1n times. In other words, you could write n by n plus 1. Now I'm going to keep the part that interests me. I have 2s in n by n plus 1. I write it below so that you have it isolated from all the other sums. 2s is equal to n times n plus 1. S is the sum of the first n numbers. As you can see, it's multiplied by 2. The 2 that is multiplying goes to the other part dividing, and therefore I will have that the sum that I wanted to calculate is n times n plus 1 divided by 2. We can then check that if n is 10, all we would have to do is to substitute n for 10 in this expression and obtain the result. Note that this would be 10 by 10 plus 1. 10 plus 1 is 11, which multiplied by 10 is 110, and all divided by 2 gives me 55, as we have seen before. We can also check that if n is 100, then substituting in this formula we would get 100 times 100 plus 1 divided by 2. That is 100 times 101 divided by 2. That's 10,100 divided by 2. And the final result is 5,050. This would then be the formula we can use to add the first n natural numbers. Let's make a few observations. To begin with, for each natural value n, the formula s equals n times n plus 1 divided by 2, which gives us a value, the sum of the values of the first n natural numbers. That is to say that for each natural number, the above formula assigns it a natural value that corresponds to the sum of the first n natural numbers. Why do I insist on this? Note that the summation formula, depends on the value n that we choose. This means that for each value of n, it gives us another value which is also natural. If you want, you can think about it, but it will always be a natural number, the sum. That is, we have somehow defined the first function among natural numbers. It is usually written in this way as s and in brackets n. Why is that? Because it means that this function depends on the value of n. Here we would put the corresponding value, or that the exercise asks us for, or that we want, and it gives us another value. That result is also a natural number that gives us the sum of the first n natural numbers. Here we have a first example of a function. The definition will come later in another new unit, but we wanted to at least give you a function to start with. We could have chosen a simpler one, but I think this one is quite illustrative. As an exercise, you can check if the above formula works for integer values of n. Remember that integer implies that they are natural numbers, but also negative numbers, including 0. And you could also test if this formula works for real values. The solution to these two exercises will be discussed in the next unit. Thank you.